say to that, other than the top thing there's a misconception in society that we think we understand what causes hypertension, and we really don't. Okay, we know some things that can cause it. So, for instance, temporary or transient hypertension, where your blood pressure goes up for a little while. Well, that's almost always stress-induced, okay? Whether it's physical stress or emotional stress. But that's not long-lasting. That just goes back to baseline after that stress is removed. Elevated chronic hypertension, the causes are sometimes idiopathic. We don't know. Like when when lay people talk and they say, oh, well, you have high blood pressure, watch your salt. You'll hear people say that, watch your salt intake. All right, and that's true. For salt-sensitive hypertensive individuals, that is true, but that's only about 5% of the known hypertensive cases are salt-sensitive. I have a brother-in-law who's salt-sensitive. He has to watch his salt intake. For most people, it makes no difference. So, regardless of what the cause is, they try to treat it with kind of the same mechanisms. They'll give you diuretics to take the fluid off of your body, and that'll lower your blood pressure. But that has all kinds of secondary symptoms. Or they can give you things like beta channel blockers for the heart that'll lower the contractility pressure of the heart, but those also have side effects, right? You get weakness and dizziness and impotency and all kinds of things like that. So the number one risk factor is actually heredity. Okay, if you have high blood pressure that runs in the family, you have to pay attention because it will probably run in your family too. My brother is hypertensive and I'm hypertensive. It's genetic, whatever the reason is. There are some things you can do to help control that. Exercise, watch your weight, proper fluid intake. Those are probably the two biggest things. Keep your weight down and your exercise level up. Secondary hypertension, I mentioned this before. Secondary hypertension is usually due to a defect in an organ. Either the organ itself has become damaged or fibrotic, or has some kind of like stones in it or something along those lines, a lot of inflammation, and then that'll make the blood pressure higher because it has to be higher to perfuse that organ. It's very common with the liver and the kidneys. Okay, you can have a renal hypertension, which is a type of secondary hypertension, usually caused by a disorder called polycystic kidney disease, where the kidney gets benign polyps to grow in it, and it makes it more fibrous and it makes it harder to push the blood through it. Congenital defects, very common where you have a narrow blood vessel or something like that where it goes through an organ, that'll cause secondary hypertension. That only puts pressure on that organ. It doesn't really stress out the rest of the body. Okay. Another pretty common form of secondary hypertension is cirrhosis of the liver, where the liver becomes kind of fatty and fibrotic, usually as a result of excess intake of alcohol over long periods of time, and that'll cause secondary hepatic hypertension, which manifests itself usually with a starburst of blood vessels around the belly button, because the portal vein, which leads into the liver, which you know what the portal vein is now, it causes hypertension in the portal vein, and so you get the mesenteric arteries and veins start to become dilated and shows up in the skin. So if you're ever at the beach and you see somebody that's got that big starburst pattern of, now I'm not talking about stretch marks from pregnancy, but blood vessels in a Medusa pattern around the blood vessel, you can just about bet that they're having cirrhosis of the liver going on. And then because Tiara asked about this, and this is the slide I must have been remembering when I was talking to you about that. Hypotension, generally speaking, hypotension, if it's asymptomatic, is fine. Okay, it's correlated with long and happy life, as long as you're fully perfusing all of your organs. Now, you can't look at your organs and say, oh, this is nicely perfused. You have to look at the metabolic effects. So, if your blood chemistries are normal, if your respiratory rate is normal, you don't have some kind of weird edema, your skin's not, swollen, you're not having dizzy spells or heart arrhythmias, then you're fine, okay? But hypotension can be an indicator of hypothyroidism. So that's one of the things to watch out for. I thought that was up here. Next slide.
No, it was on the last one.
It was on the, okay. Anyway, hypothyroidism can contribute to low blood pressure. So that's one of the warning signs of that. Few definitions, I think. Yeah. Orthostatic hypotension, we've all experienced this at one time or another. This simply means a change of body position linked to a little bit of dizziness. And as you get a little bit older, this becomes more common. So if you got out of bed too early in the morning, you're like, whoa, a second, okay, that's orthostatic hypotension. What's primarily responsible for keeping cardiac output up when you stand up? Remember the mechanism? What's responsible for that? Well, we're dancing around the right idea. Yeah, the muscles compress the blood vessels, send the blood back to the heart, and that's Starling's law. You increase venous return, increase preload, degree of stretch in the ventricles goes up, and ejection goes up. So cardiac output goes up immediately. So poor vascular health usually is associated with orthostatic hypotension. It means you go to get up and you're dizzy.
Will it cause poor vascular health? Like it's not dehydrated and stuff?
Well, that's not vascular. Really, sedentary lifestyle. Just not using your vessels for exercise very often. Obesity also puts a lot of stress on those vessels. Now, some people have poor vagal tone also, where their medulla oblongata, which has the vasomotor center in it, which communicates via the autonomic nerve known as the vagus nerve to your blood vessels. That mechanism can actually be defective from a congenital standpoint. It means you're born with a poor response. So those people are always going to have syncopal episodes, and they kind of have to watch out for that. Or it could actually become damaged. Anesthetics are going to make that slow to respond, like that temporarily. Now, acute hypotension, this is usually the result of injury, and you have massive vasodilation, so your blood pressure drops. If your systolic blood pressure drops much below 60 systolic, usually you can't stay conscious at that, and you'll pass out. And that, if it doesn't correct itself.
Not like a loss of blood, like you got cut or.
Right, so that would be hemorrhagic shock. You could have septic shock, but in pretty much all cases, what makes you pass out and potentially kill you from shock is a loss of blood pressure. That'd be acute hypotension. Well, the name of the game then, getting into the next point here, the name of the game is tissue perfusion. Okay? Tissue perfusion. This simply means filling the capillary beds of an organ with blood. That's what tissue perfusion means. Filling the capillary beds of an organ with blood. Tissue perfusion. All of your organs have a certain perfusion rate that they must meet in order to stay healthy.
Filling your capillary beds with...
In a particular organ, making sure the capillary beds of a particular organ are full of blood. Now, for some organs, the perfusion rate is pretty steady, like the heart. Okay? The heart is being perfused at about 85% its capacity all the time. The brain. Similarly, the brain is functioning about 90% capacity all the time. So in those organs, there's not a big margin for error. If you drop that perfusion rate down, you start to suffer the consequences. You start to suffer ischemia, which means loss of oxygen, and tissue damage. Okay? So some of your very, very sensitive organs to this kind of thing are cardiac muscle and the brain. Then you get some intermediate ones like the liver and the kidneys. They're fairly sensitive to this sort of thing. And then you have ones that have a wide variety, like skeletal muscle. When you're not using a skeletal muscle, its perfusion rate is probably around 5% of its max. But when you're using that muscle, that jumps up to 90, 95%. It takes a huge amount of blood to perfuse those muscles when they're working optimally. This, of course, explains, at least in part, why it's so hard to focus mentally on something when you're doing a physically demanding task. The brain is actually being a little deprived of oxygen, and it makes it a little harder to think. And so when you're using all those skeletal muscles and diverting the blood and oxygen to those, the brain gets a little fuzzy, you know? Okay. Likewise, kind of same thing when you eat or drink a big meal, okay? Ordinarily, the gastric capillaries, I couldn't give you an accurate number, I'd probably say around 15% what they could maximally hold. Then you eat a big meal, and that goes way up. You know, triples or quadruples its blood supply to the stomach. That's called gastric steel. It takes the blood supply away from other things. Well, how do you feel after a big meal? You feel tired and sleepy, right? The brain's kind of like, you got this, and shuts off, you know, says, okay. And you go take a nap or something until you do the digestion. By the way, when grandma or mom told you don't go swimming after a big meal, okay, and of course then they tell you that's because you're going to cramp up and drown or something like that, well, you're not going to cramp up and drown. What you're going to do is you're going to get a sour stomach. You're going to go swimming, the skeletal muscles are going to divert that blood away from the stomach, and you're not going to digest the food that's in there. It's going to sit there, it's going to become kind of rancid and cause irritation, and when you get back out of the pool 2 hours later, you're probably going to throw up, okay, because it's been sitting in there all that time. So all that does, it just causes poor digestion. Right? Your body's not stupid enough to digest a hot dog and then let you drown. It's gonna prioritize the skeletal muscles. Now, the last bullet point there, the rate of flow is precisely the right amount to provide proper function. Usually I tell students, look, you would need at least twice your blood volume to fully perfuse all of your organs all the time. Okay? So we're not doing that. We're not perfusing our kidneys and our stomach and our liver and our gonads and our brain and our lungs fully all the time, because we're not using all those organs maximally all the time. So we're selective about that. We have about 5 liters of blood. You would need somewhere between 10 and 15 liters of blood to perfuse everything all the time. All right? And that'd be a waste. We don't do that. So how do we regulate it? I'll get to that in a second. Nothing on this graph you have to memorize. Here we are in figure, they told me they fixed this. Just so you know, I submitted a trouble ticket. They came in and said they fixed the resolution of the screen. It's clearly not fixed.
1913.
Anyway, it's figure 1913. It's cut off at the top. What they're showing you here is the change during exercise versus non-exercise. So the brain, I don't know if you can quite see it, but the brain's at 750 mils per minute, and that doesn't change during exercise. So that's pretty much fixed. The heart, that goes up a little bit. Here's at 250, and then under vigorous exercise, it triples, goes up to 750. But look at skeletal muscles. So at rest, all of your skeletal muscles are taking about 1,200 mils, and that represents just a little bit more than 1/5 of your total cardiac output. But during intense physical exercise, that goes up to 10 times. 10 times. Well, that's got to come from somewhere. It can't increase the amount of blood you have, so it takes it from things like the kidneys, okay, which go way down, the abdomen. See, there's your abdominal fraction, that goes way down. So that's the idea of, don't go swimming after a big meal. And then one doesn't, it's in the abdomen here. You have an organ right over here on the left side. What organ do you have over there that you only have one of, not two of? No, pancreas is a good guess. It starts here and goes over. Spleen. You got a spleen over here. Okay. Well, the spleen is one of those organs that sometimes students walk out of A&P going, I still don't know what it does. All right. There's a funny YouTube video if you want to watch it. It's a little song somebody made up called "What Does Spleen Do?" It's kind of funny. A couple of medical students that I guess were bored. Anyway, the spleen filters blood. Essentially, what it does. It filters damaged red and white blood cells out. But it's also a reservoir for blood. Okay, the spleen can dilate, and it's a fibromuscular organ, so it's basically a big pouch over here that has a lot of blood in it. When the body needs more blood, it contracts and sends that blood back into the circulatory system. So it's kind of a reservoir for blood. All right, velocity of blood flow. It's a confusing graph, and basically all it says is that the speed with which the blood flows through a particular vessel is dependent on the diameter of the vessel. So that's the speed at which it flows through a particular vessel. Now the speed with which it flows through the vessels is actually a function of all the vessels of that size in your body. So these two can be a little bit confusing. So in an individual capillary, now don't write anything, just listen. Okay, just listen. If I had one aorta go to one muscular artery, and that went to one arterial and to one capillary, in order to accommodate the amount of blood that's flowing, how fast would the blood have to flow through the capillaries? Faster or slower than it did in the aorta?
Can you repeat that?
Yeah, okay. If I just had one capillary, one arterial, one muscular artery, one distributing artery, one aorta, okay? So just all linear. So here I'm injecting 5 liters of blood. Well, yeah, let's just leave it at 5 per minute. What would be the rate of flow in the aorta versus the capillary?
Faster in the capillary.
So in the capillary, it would have to be a lot faster because it's much smaller. So to accommodate that same flow, it would have to go a lot faster through the capillaries. Now, is it surprising to find out, if you look up there, what's the velocity of flow through capillaries?
Slower.
It's a lot slower. So that seems a little counterintuitive, okay? But the reason is you have millions and millions of capillaries, okay? So it's a function of not just the one vessel, but all of the blood vessels of that type. Right? So we call that the total cross-sectional area. So you've only got one aorta, and its cross-sectional area is about 5 square centimeters. which is huge for blood